Hi everyone, this is Mr. Islami speaking. In this video, I'm going to talk about the projectile motion, which is the lesson 3 of Unit 1, Dynamics Physics Grade 12 course. Okay, so let's get started. The first thing that I want to mention is, the first question is, what is the projectile motion? So as you can see, the projectile motion is a motion of an object that is launched from any height with an angle of 0 to 90 degrees. Okay, so in the first diagram, as you can see, there is an object that is being launched from the ground with an angle of theta and with an initial velocity of vi. In the second diagram, it's the same thing, but the only difference is that the object is launched from a height. And the third diagram, this is another scenario that you can launch. If you are launching from a height, you can have the angle of 0, which is called the horizontal launch. But of course, on the ground, we don't want to launch from 0 degrees. It doesn't make sense. The other thing, can I have 90 degrees for theta? Yes, but that's kind of the previous lesson. It's the vertical motion. So in this case, we don't want to discuss about the 90 degree one. Okay, so the very important fact about projectile motion is that this is a motion that is happening in 2 dimensions. So it's a 2-dimensional motion. So what I mean by that, if you look at this, the same kind of projectile motion that I have here in this diagram, if I say the starting point is A, the top point is B, and the last point is C. If I go from A to B, the directions that I'm going is to the right and up. So as you can see, 2 directions or 2 dimensions. And then from B to C, again, I'm going to the right side, but this time I'm going down also. So again, 2 dimensions. So the very important thing about the 2-dimensional motion in the projectile motion is that in the horizontal direction, which is usually called the x direction, the acceleration is 0. And the reason is that as you guys know, we do have the gravity going down, or let's say towards the center of the earth. So that's why in the horizontal direction we do not have any acceleration. And also we know that if there is no acceleration, that means the motion is with constant velocity. So this is something that we should keep in mind. In the vertical direction, though, we do have acceleration, and our acceleration is, as you guys know, our acceleration is going to be the g, which is almost 9.8, or to be more exact, 9.81 meters. Okay, so as you can see, we have a simulation here. So what I want to show you guys first is the acceleration vector. So I'm going to launch it right now. So let's see what happens. So as you can see, as the object is moving, there is an arrow, the yellow arrow, going towards the ground. That shows the acceleration. And as you can see, as the object moves, this vector is not getting shorter or longer. So that means it's constant. So if I continue, as you can see, until it reaches the ground, it's all the same. Okay, so now I'm gonna remove that acceleration vector, and now I want to discuss about the velocity vector and specifically the components. So let's do it one more time. Okay, so my angle is also 40 degrees. I can adjust all of these, but I'm not talking about the numbers here. I just want to explain the concept here. Okay, so as I launch, as you can see, there's 2 green arrows. So what are these 2 arrows? These arrows together will show your velocity, which is this vector, the vector that you can see right now, the green one. So why do we have those 2 components? So technically, these 2 components are the x and y component of the velocity, because this is a 2-dimensional motion, as I mentioned. So As the object is going up, as you can see, the vertical component of the velocity is getting smaller, and the other one is fixed. It doesn't change. So I want you guys to focus on the horizontal one for now. See, it doesn't change. It's all the same from the beginning. I can show you one more time. Just focus on the horizontal one. As you can see, the horizontal one is always the same because there is no acceleration, so velocity should be constant. That makes sense, right? So how about the vertical component? If I launch this again, so now this time let's focus on the vertical one. So first of all, oops, I launched too nice. Okay. So first of all, you can see in the beginning it's pointing up because the object is going up, right? And it gets smaller until it's almost zero because it reaches the maximum point where the object is not going up and down. It's like a turning point. Then after it reaches the maximum height, after that, as the object moves down, the arrow actually points downwards. Okay, and it gets bigger because as the object comes down, the velocity, the magnitude of the velocity in the vertical direction is getting bigger, right? And until it hits the ground. Okay, since I discussed about the components of a vector, I just wanted to have a quick review on vectors and how to find the components of a vector. So in this diagram, as you can see, there is a vector with an angle of theta with x axis. So how do I find the components of this vector? It's very easy. I assume that most of you guys know how to do it, but just in case, I want to just explain very quickly. So what you do, you can have your x component or the horizontal component like this, and I'm going to call it Vx. And I can have my vertical component, which is going to be something like this. I'm going to call it Vy. And these two together, this Vx and that Vy, also Vy, I can sketch it here also. It doesn't really matter because they are the same. They will create the V vector. So the relations that we have here is if you want to find the magnitude of vector V, it's going to be the square root of Vx squared plus Vy squared. And this is technically coming from the Pythagorean theorem, as you can see. But the other important thing is if you want to find Vx using V and theta, if you use just basic trigonometry, is going to be the magnitude of V, which I'm going to show you with just V times cosine theta, and Vy is going to be V sine theta. Just keep these, especially these two, because we're going to use them in the next section. Okay. So now we have to discuss about the projectile motion formula. So as I said, the x direction, our motion is constant velocity. So acceleration is 0. So that means we only have one formula, which is here. Delta x is your displacement in the x direction. So from here on, we're going to show it with delta x. It's just easier. What is Vx? Vx is the x component of V, which is constant. So there is no initial or final. It's all just the same. And as I mentioned, Vx is going to be V cosine theta, and that V should be the initial velocity. But Vx at any point is constant, as I mentioned, and delta t is just time. For the y direction, in these formulas, which I'm not going to explain because they are exactly the same formulas, I just want to mention about the Viy and also the Vfy here, because these are the only ones that are different. So Vi1 means the y component of the initial velocity. How do we find it? Whenever you want to find Viy, it's just Vi times sine theta because it's a y component. So the first example, it says a small ball is thrown from ground with an angle of 30 degrees and an initial velocity of 20 meters per second. Find the following horizontal range and maximum height. Okay, first of all, let's sketch a very simple diagram for this situation. So what is happening is we have an object on the ground, and then we're going to launch it with VI of 20 meters per second, and it's going to travel like that, and it will hit the ground eventually. The launch angle is 30 degrees. Okay, so we want to find the horizontal range, which means we are looking for this delta x, and also we are going to find the maximum height, which is here, and I'm going to show it with h max. Okay, so let's do part A. How do I find delta x? So if I go back to the formulas that I have, the only formula that has delta x is the one on the left side. Okay, so let's use that. So delta x is Vx times t. Instead of delta t, I'm going to just use t because it's easier. So do I have delta x? No. Do I have Vx? I know that Vx is Vi cosine theta t. Okay, so let's substitute the values that we have. Do I have Vi? Yes, it's 20. Do I have theta? Yes, it's 30 degrees. Do I have time? No. Okay, so far I know that delta x, which I'm looking for in part A, is going to be 20 cosine 30 times t. Okay, so 20 cosine 30 is root 3 over 2, so it should be 10 times 1.73 t. Yeah, so that means delta x is going to be what? It's going to be 17.3 t. Okay, so I have to keep this for now. So this formula, as I mentioned, it was in x direction. So could I solve it? Could I solve what the question was asking me? No, because I need to find t. So if you need t, that means you have to use the y direction as well, and see what we can do in the y direction. Okay, so on the diagram, if I call the initial point A and the last point B, if I ask you from A to B, what is the displacement? What is the vertical displacement? Because we're talking about the y direction. The vertical displacement, as you can see, it's 0 because we started from the ground and we ended on the ground. So that means delta y is 0. So the formula that I can use is going to be the first one here, this one. I'm going to use that. So this is 0 equals VIY is going to be VI sine theta. So 20 times sine 30 times t plus 1 over 2. G, because it's towards the ground, so I can put a negative. I mean, I have to put a negative because the down direction is negative. So I can solve for t here. Factor out the t, so it's going to be t times 10 minus 4.9 t equals 0. It will give me two values for t. One of them is 0, which is not wrong because it's technically the starting point, and then the other one, which I'm going to use, is going to be, if you do it with your calculator, it should be 2.04 seconds. That's the time. Okay, so now what I can do, I can replace this time here and then find the delta x, which is the answer. It should be 35, around 35.3, I guess, meters. So that's going to be the answer for part A. And part B, it says find the maximum height. What I can do here is to find the h max, I have to go to the y direction, right? So what I can do, I have this as 30 degrees and initial velocity is 20 meters per second. Okay, so I'm going to use the delta y formula. So delta y was VIYT plus 1 over 2 GT squared. Okay, so delta y is the displacement in the y direction, which is what I want to find is h max, because if you go from A to C, your delta y is h max, right? So VIY is 20 times sine 30 degrees times t. Okay, so that's the tricky part. T, I cannot use the t that I found 2.04 here. I cannot use that. The reason is that time is from A to C. That time is 2.04 seconds. So A to C, you can kind of guess it's half of the motion, and this motion is completely symmetrical, so you can actually divide this by 2. So this time is 1.02. So I can use that time for t here. So 1.02 plus 1 over 2, again negative 9.8, and again 1.02 squared. So if you just put these numbers in a calculator, the maximum height that you get, it should be around 5.1 meters. Okay, now example number 2. So it says a pumpkin is thrown from top of a building with an angle of 30 degrees. So let's actually make a sketch of this scenario. So we have a building which is 8 meters high, and then we are going to launch a pumpkin with an angle of 30 degrees. So it's going to be something like this. And there is a target on the ground, which is how much? 18.6 meters away from the building. Okay, here 18.6, 30 degrees, and 8 meters is the height of the building. It says at what velocity should the pumpkin be thrown so that it hits the target. So technically what it's asking for is VI. So we need to find VI. First of all, in the horizontal direction or X direction, what we have is the range. The horizontal range is 18.6. Okay, so this is the formula that I can use, VI cosine theta t. Okay, so I have 18.6. VI I don't know. Cosine 30 degrees. And t, I don't know. So I get 21.5. Okay. Okay, so I need to go to the y direction as well. So what do we have in the y direction? The y direction, we know that the displacement from point A to point B, if you look at it vertically, there is 8 meters going down from A to B. Okay, we don't care about the horizontal distance. All we need to care is the vertical displacement. And I don't care how much the ball, or sorry, not the ball, the pumpkin is going up, because displacement is about the initial and the final point, and finding the direct distance between them. Okay, so delta y, 8 meters going down, so negative 8, equals VI, I don't know. Sine theta is 1 over 2 because it's sine 30 degrees. And t, we don't have it, plus 1 over 2, negative 9.8 t squared. Okay, so now I need to solve for t, right? So what do we do is, do you see the VI and the t here? They are multiplied by each other, right? I can replace it with 21.5, and that should just make this very easier. It's going to be 21.5 times 1 over 2 minus 4.9 t squared. Okay, now I have to solve for t, and if I do the math here, at the end I should get 1.95 seconds. So as you guys know, I can replace this t and then put it in this equation to find VI. So VI is 21.5 divided by t, which is 1.95. And this should give me, if you actually use your calculator, it should be around 11 meters per second. Okay, so now I'm going to show you if my calculations are correct. So okay guys, as you can see, I have set up this simulation exactly based on the question that we had. So the height is 8 meters, the angle is 30 degrees, and if you look at the left bottom corner, the initial speed is 11 meters per second, and I have placed a target in 18.6 meters away from this cylinder or building or whatever it is. So I'm going to launch it. It should fall exactly on the target if my calculations and my equations were correct. Okay, so you guys ready? Let's see if it hits the target or not. Okay, I'm kind of nervous, but let's see. Okay, I'm going to show it in slow motion. Ready? 1, 2, 3. Let's do it. Ooh. Okay, yes, exactly. 3 star because that was exactly in the middle, and that shows that all my calculations were correct. So that's good. So I hope you guys understood this lesson, and in the next few lessons we will do more questions about projectile motion.